Hello and welcome. My name is Ian, and in this video, I'm going to be talking about theoretical distributions and the idea of sampling and how we can use Monte Carlo simulation both to better understand what a distribution is and where data comes from, and also to do useful things and predict things that might be hard with traditional mathematical techniques. So let's start with kind of philosophical question. Where does data come from? If we think about a coin flip, let's say we have a perfect coin here with 50-50 probability. And what we want to know is how does this coin, this perfect unbiased coin, how does it lead to so-called imperfect data? For example, we do 100 flips and I get 55 heads results and 45 tails results. And why did we get this kind of imperfect result? We said it's a 50-50 probability, right? It's a perfect coin. So why don't we just get 50 heads, 50 tails? And where does the randomness in random data come from? To kind of figure this out, let's go back to another example, actually. So instead of the coin, let's consider rolling 2 dice. So we have 2 fair dice, and the result of a particular experiment is going to be the sum that we get from those 2 dice. So if we roll 2 ones, then the result is 2. If we roll 2 sixes, then the result of that would be a 12. And let's go through and just enumerate all the possible events that you could get from a 2 dice roll. So starting with rolling 2 ones or a sum that is equal to 2. And so something I could ask you is are you more likely to roll a 2, net 2, in other words, a 1 and 1, or are you more likely to roll a net 3, 2 dice whose sum is 3? So the answer, of course, is you're twice as likely to roll a 3. And that's because you have 2 possibilities. You can either roll a 1 and a 2 with the first die and the second die, respectively, or you could roll the reverse. You could get a 2 and a 1. Both of those would lead to the result, a net 3. In the case of a net 4, you have 3 ways you can get a net 4. You could roll a 2 and a 2, a 3 and a 1, or a 1 and a 3. And we can keep doing this then for all the possible results. We see that there are 6 ways that you can roll a 7. So you can either get a 4 and a 3 and a 4, a 5 and a 2 and a 5, a 6 and a 1, or a 1 and a 6. And we do this, enumerate all the different possibilities, all the way up to 2 sixes or a net 12. And if we count these, we'll see that there are 36 in total. Another way we could have found that is by taking 6 to the second powers. And that's going to give us all the different arrangements that's possible for two things with 6 possibilities. And look what we have here. So if we take a look at the shape of this diagram here, where we've enumerated all the possible events or outcomes of this experiment, we start to see this bell-shaped curve emerge. And if we go through each of these columns and just count the number of events, so in the case of the net 2, there was 1 event corresponding to a net 2, and there are 36 possibilities here. So we can get the probability of this event, right? It's 1/36. We can do that again for the net 3. So there were 2 possible ways to roll a net 3. So its probability is 2/36. And we can do this again for all of the different possibilities here, with the most likely result being rolling a net 7, which has a 6 out of 36 probability of occurring. And if we compute this number, it's decimal, then we'll see that we have a value of 0.16, which we can remember. And so what we've done here is we've created a probability distribution. And a probability distribution is a kind of theoretical idea, or it's an ideal distribution that is distinct from, say, a frequency distribution of data or a histogram of data, because in this case, this is the distribution. This is the frequency distribution of possible events. So it represents something slightly different than, or fundamentally different than the distribution of results that you get from an experiment. And there are a few features that you need for it to be considered a probability distribution. So one of these is that everything has to sum to 1. If I were to add up the area of these bins, like if I have a variable on the x-axis and I multiply each of those with the heights of these bins, then this must sum to 1. If I have, let's say we're looking at a coin flip, and I'm considering the two options, we can get a heads or a tails. The probability of heads plus the probability of tails needs to represent the probability of all the possible events. If there are just these two events, then those need to add to 1. And you can have this with frequency distributions as well. They can also sum to 1. So you can have a normalized frequency distribution, and we can, for example, kind of compute or convert things into something like a probability distribution by this process of normalizing or dividing by the sum. But there's still a distinct difference between data and probability, and that is the fact that we're sampling this space when we're gathering data. And so even though there were 36 possibilities, 36 possible outcomes for the two dice roll, if we actually perform 36 experiments, and so here I set up some code that does exactly this, right? We have a random choice that's going to pick a number from 1 to 6, and then do this twice, pick another number from 1 to 6, and then sum these together. If we do this 36 times, we get a distribution, for example, that looks like this. And this does not look like the perfect distribution that we enumerated in the first slide. But what we'll notice is if we do 1,000 rolls, now we start to see something that looks a bit more like it. And we start to see this peak occurring at 7 or near 7, which we said was the most likely result. And the more we do these experiments, the more likely events are going to occur more frequently as well. And then if we go all the way up to 100,000 rolls, now we see almost perfectly symmetric distribution that has a very similar shape to the one we mapped out. And in this case, we performed 100,000 events, and we got approximately 16,000 results corresponding to the 7 event. And when we divide this by n, or 100,000 in this case, we got this value here, 0.16. And if we remember, that was the probability that you would roll a 7, net 7. And so this highlights an interesting law of probability, the law of large numbers. And this is the idea that as our sampling goes to infinity, the shape of our frequency distribution, or features of our frequency distribution, are going to trend towards their theoretical counterparts. And so this is true with the distribution itself. It's also true with, for example, the mean. So if we were to just track the mean, our observed mean, so x bar here, versus the theoretical mean. So if we took the mean, which if you remember, we can do this for binned data. We could do that for the enumerated 36 possibilities and get the mean, the theoretical mean of the perfect theoretical ideal distribution. And then we can just compare that. So as we sample more data, we perform more experiments, and each time we take the sample mean, we will see that the larger our sample is, the closer this observed mean is going to be towards that theoretical one. And so this is called the law of large numbers. And what it gives us is a very useful tool, which is that even if we do not know the shape of the ideal probability distribution, we can use experiments to get a lot of information about it. And a good example of why you would want to do this is, so in the case of the 2 dice throw, we were able to enumerate all 36 possible results that you could get. But suppose I threw at you 112 dice roll, and I want to know what is the probability distribution of the net result, or the sum that you would get from 112 dice throws. Well, we can use that same power formula to compute the number of possible results. So 6 raised to the 112th power. And that is going to give us 10 to the 87 possible results. And for reference, there are between 10 to the 78th and 10 to the 82 atoms in the universe. So here we have more possible results than there are actual atoms in the universe, which means that enumerating, using the strategy of enumeration that we did for the 2 dice throw is simply not going to work for the 112 dice throw. But what we can do is we can sample. So what we can do is, so here's for 5 dice throw and 100,000 experiments, we've generated this distribution. For 112 dice throw, here we can do just 200,000 experiments, and this gives us a really good idea of the shape of the distribution. And you can see there is some noise here. If we were to up this number to 2 million experiments, then we would see some smoothing out here. But you can see that even with just 200,000, which, okay, this is a large number, but it's much smaller than 10 to the 87. We already have a ton of information. We know approximately where the peak of this distribution is occurring, the mean, and we know the shape that it's taking as well. And so this is the Monte Carlo method. It has an interesting history. So it was invented by Polish-American scientist Stanislaw Ulam, and he was playing solitaire games in a hospital and wondered what was the probability that you would get a winning hand in solitaire. And he tried initially to compute this through combinatorics. So, like we did with the dice throw, try to enumerate the possible hands that you could get in solitaire, and realized that this was a very complicated problem, and it's very hard to do this, and that it would actually be easier to simply simulate millions of solitaire hands on a computer. And so that was the original origins of this technique. And it relies on random number generators. So computers sometimes have trouble with this, but we have methods to approximate truly random numbers. And while these methods are imperfect, for many cases, they are good enough for what we want to do. So we have, they're called pseudo-random numbers. And we can use this to generate, for example, random numbers on an interval between 0 and 1. And so this can be extremely useful for some very practical problems. So an example from the lab might be this proximity ligation experiment. So this is a kind of attempt at a realistic example for someone who's doing molecular techniques in life science. And proximity ligation assay is a technique where you're trying to detect if two things are close to each other in space. And so for this example, we're just going to say that we have some molecule A, and it's going to activate when it's within some critical distance, r equals 0.4 units away from molecule B here. So we have the black dots molecule B and the red dots molecule A. And what we just want to know is, what's the probability distribution of distances between A and its nearest counterpart B. And then if we can get that, what is the proportion of A molecules that are going to be activated? So if I give you a particular density of A molecules and B molecules, what's going to happen? And so this kind of simple question is deceptively difficult if we take a kind of calculus or algebraic mathematics approach. And so this is going to require that we know a lot about, have some analytical expressions that represent how points can be distributed and how their distances are distributed. And it may be that we do not actually know how to do this. And what we can do in that situation is apply a Monte Carlo approach. And this is much simpler because what we can do then is simply, if we look at this piece of code here, we just generate a random number from 0 to 1 for an x coordinate, and we generate a random number from 0 to 1 for a y coordinate. And we can do this according to some density, so we can specify how many points we want to make. And we just generate a bunch of random points. And using Euclidean geometry, classic geometry, we can take any 2 points and compute the distance between them. So we take x1 minus x2 squared plus y1 minus y2 squared. Square root of that is going to be the Euclidean distance for this 2D, 2 points in 2D space. And what we can do is just do this for all the different points that we generated, A points and B points, and we can throw it into a histogram, and we can answer a question. For example, if we said the critical distance was 0.4, then this data gives us the answer. We can just check, how many points fell below that, and that would give us the fraction of activated molecules. So this example may be a bit specific, but it illustrates an important point, which is that you can use random number generators and computers to get a lot of information about any particular distribution, as long as you can replicate the generating process behind that distribution. And you may not know math or analytical expressions that describe that process, or they may be even impossible to derive. But using these computational techniques, we can get a lot of information. And as a result, this is an extremely powerful and legitimate and useful approach to scientific modeling that's used all the time. Yes, so to summarize, so we have this idea of enumerating all the possible examples. We call this the population. So for example, all possible games of solitaire, all possible combinations of a 2-dice throw. And if we look at the proportions of these events, then that's going to give us the probability distribution. And sometimes you can enumerate all the possible events, but in most cases, it's not possible. And that's where experimentation comes in, sampling. So we're sampling, performing experiments that allow us to get information about the shape of that distribution. And sometimes experimenting can be done in a lab, but sometimes it can be done in a computer. And that's the Monte Carlo method. When we have data that's derived from a population, we'll sometimes represent that with a histogram or a visualization of the frequency distribution. And as we increase their sample size, thanks to the law of large numbers, those histograms or frequency distributions are increasingly going to look more and more like the underlying true probability distribution. So that's all I had. Bye-bye.